Hello students, in today's class I'll be starting this new topic, that is principle of continuity. Now it states that when an incompressible and non-viscous liquid flows in a streamlined flow. Now as you already know, streamlined flow is a flow where liquid flows with a constant velocity in one certain direction. Okay, there are two types of flow. One is streamlined flow and other one is turbulent flow. I'm talking about streamlined flow, where each particle passes through a certain point, follows the same path as the preceding particle. Okay, that is a streamlined flow. Now according to this principle of continuity, when an incompressible and non-viscous liquid flows in a streamlined motion through a tube of non-uniform cross-section, then the product of the area of cross-section and the velocity of the flow is same at every point in the tube. So it might sound confusing, but over here what you can see in the diagram is that now this tube is of a non-uniform cross-section area. That means the area over this point X and this area of the pipe over this point Y is different. It's not the same. The area is different. So the product of the area and the velocity is same at each and every point in the liquid according to this principle. So that is what we have to prove. Okay, that is product of the area, cross-section area, and the velocity of the flow at that point. So over here at the point X, you can look at the diagram. At the point X, the velocity of the liquid is V1, where the area of cross-section is A1. Now similarly at point Y, the velocity is V2 and area is A2. Now the volume at point X. The volume at point X is A1 into V1. That is the volume at the volume of the liquid passing through that certain area is A1 into V1, and the volume at the point Y is A2 V2. Now mass is density into volume. Density is represented by rho and A1 V1 is the volume. Similarly, mass for this point Y is rho into A2 into V2. With this, you can look at this one. According to this theorem, what is said is that the product of velocity and cross-section area is same at each and every point. So that is what is written over here. Now the liquid which enters at point X must leave from the other end Y. Hence, the mass which is entering at point X will be the same amount of mass which is leaving through the point Y. According to that, the mass at point X is this one, mass at point Y is this one, which is equal, which will be same. Now from here, density gets cancelled because it's the same liquid which is flowing, density becomes the same. So from here, what we can see is A1 V1 is equals to A2 V2. So each and every point, area and velocity is constant. So now over here, there is a diagram of a tube where the area is smaller at the center. Now thus at every place in the tube, the product of the area of cross-section of the tube and the velocity of the flow of the liquid is a constant. Therefore, the velocity of a liquid is smaller in the wider parts of the tube and larger in the narrower parts of the tube. So this is what you need to remember. So according to this diagram, if this is a wider part of the tube, the velocity at the wider part of the tube will be smaller, and whenever the liquid reaches a narrower part, the velocity increases. So that is what happens, and according to that, this area into velocity remains constant. Okay, this is principle of continuity. Now remember this, the velocity at the narrower part is lesser than the velocity at the narrower part is larger than the velocity at the wider part. Okay, now next is different energies of a flowing liquid. As we are studying about the flow of the liquid, so we need to study about the different types of energy which it possesses when it flows. So first is pressure energy. Now let P be the pressure on the area of the liquid, with area is the A, and the liquid moves through a distance L due to this pressure. Okay, we are assuming the distance to be L. Now energy is equals to work done. This is what we know. Energy is same as the work done. Now work done is force into distance. F into D is the work done. Now what is force? Force is pressure into area. Okay, so in place of pressure I'm writing P, area is A, and distance is the distance the liquid which is traveling is L. Now the volume of the liquid is A into L. This is the volume of the liquid. Area into the length of the liquid which it is traveling. Now pressure energy per unit volume. Pressure energy per unit volume is pressure energy is PAL and unit volume is A into L. So AL gets cancelled. What we get is P. This is the pressure energy of a flowing liquid. This is the first type of energy which a flowing liquid possesses. Now the second is kinetic energy. So let us assume m is the mass of the liquid, v the volume, small v is density, okay, capital V is the volume. Now kinetic energy is half mv square, as you already know. Now kinetic energy per unit volume of the liquid will be half mv square divided by volume. Okay, it is per volume of the liquid, so it is divided by V. Now as you know, density is equals to mass into volume. So in place of mass divided by volume, we are writing density. Density is mass divided by volume. So in place of density, in place of mass per volume, I am writing density. So this is what we get. This is the kinetic energy per unit volume of the liquid. Now the third type of energy which a liquid possesses is potential energy. For that, let m be the mass, h be the height of the liquid from the surface of the earth. Potential energy is mgh. Now potential energy per unit volume is mgh divided by v, that is the velocity, volume. Now as again m divided by v is density, so rho gh is potential energy per unit volume of the liquid. So I've just told you about three different types of energy, that is pressure energy, kinetic energy and potential energy. So keeping that in mind, we'll move on to the another topic, that is Bernoulli's theorem. Okay, according to this theorem, when an ideal fluid flows in a streamlined motion, then at every point of its path the total energy per unit volume is constant. So I'm talking about ideal fluid, which is again incompressible and non-viscous liquid or gas. Fluid is either liquid or gas which is incompressible and non-viscous, which is flowing in a streamlined motion from one point to another. Then at every single point the total energy will be conserved or constant. What energy I'm talking about? The energy are pressure energy, kinetic energy and potential energy. That is per unit volume. Okay, not only energy, it is energy per unit volume. So pressure energy was P. If you remember the slides before which I've shown you, pressure energy is P, half rho v square, this is kinetic energy, and rho gh is potential energy. This sum of all the three energy will be constant at each and every point of the flow of the liquid. So next I'm going to show you this diagram over here. Now this is the diagram where the pipe, you can see it is from x to y. Okay, from point x to point y there is a pipe where the area of cross section is different, where A1 is greater than A2. Slowly the area is becoming smaller and smaller. The pressure at x is P1, pressure at y is P2, velocity at x is V1, and velocity at x is V1 and y is V2. So what I'm trying to say is, at each and every point, pressure, area, velocity is changing, and also the height, that is at h1 and h2. So at each and every point, pressure energy, kinetic energy, and potential energy is changing. But if you add all the three different types of energy, it will remain the same. It will remain same at each and every point, but it is different at, but if you consider one energy at one point, so for example take kinetic energy. Okay, kinetic energy at x will be different than kinetic energy at y. Now why is that so? Why kinetic energy is different? It is because the velocity, kinetic energy is mainly because of the velocity. Now velocity at v1 is different than velocity at v2. Now velocity v1 will be at a wider space, the velocity will be smaller, and in the narrower point, that is v2, velocity will be greater. So velocity v2 is greater than velocity v1. That is why velocity at x and y will be different. It is slowly increasing. The velocity is slowly increasing. That is with velocity. Now pressure energy. We are talking about the pressure energy. Pressure energy P at P1 and P2 will be different. It is mainly because of the area. Okay, pressure energy is different, which is because of the area. Now the third one is the potential energy. The potential energy is because of the height. So at the point x1, h1 is larger. At the point y, h2 is smaller. Compared to h1 and h2, h1 is greater than h2. So directly what we can say is, potential energy at point x is larger than the potential energy at point y. So this way every energy changes at every single point, but overall it is always constant. So this is what Bernoulli's theorem is about. Again I'll tell you the statement, that is, when an incompressible and non-viscous liquid or gas flows in a streamlined motion from one point to another, then at every point of its path the total energy per unit volume is constant. So total energy means pressure energy, kinetic energy, and potential energy per unit volume remains constant. The proof of this theorem is actually not required, so just understanding of this theorem is enough. Okay, with this we will talk about few examples or applications of Bernoulli's theorem. First one is Bunsen burner. I hope you have seen this in the lab. The Bunsen burner consists of a long tube having a fine nozzle O at the bottom. Okay, from this bottom the gas will enter. The burning gas enters the tube through O and burns in a flame at the top of the tube. To produce a non-luminous flame, the air of the atmosphere is mixed with the gas. Okay, you can see a small hole over there where the air enters, and it is getting mixed with the gas so that it produces a non-luminous flame. Since the nozzle O is fine, the gas enters with a large velocity, and so the pressure inside the tube is lowered than the outer atmospheric pressure. Therefore, Air from outside rushes into the tube through a hole and is mixed with the burning gas. So with the very small nozzle over here, what happens? The gas which enters with a very high velocity. Okay, this is the first example. Second one is atomizer. This is an instrument used to spray a liquid in the form of small droplets. It consists of a vertical tube AB whose lower end A is immersed in a liquid filled in the vessel, and the upper end B opens in a narrower part of a horizontal tube. At one end of the tube there is a rubber ball, while at the other end there is a fine bore. When the rubber ball is squeezed, it sends a stream of air which passes through the tube. The velocity of the air is very large in the constricted part of the tube, so that the pressure in that part is lowered. Consequently, liquid rises in the tube AB and is mixed with air and comes out in the form of fine spray. The atomizer is used to spray colors and perfumes, to color motors, to spray water on hairs, and to wash air nose, something like that. So this is a device used frequently. So these are the few examples of Bernoulli's theorem and instrument based on those theorems. So this is the final topic of the chapter. One topic is left which is not there in the syllabus. We are just going to exclude that. So in the next class I'll be starting a new topic and a new chapter. Okay, this much for today. Thank you.